All right, welcome back. Today, we are diving into what is, without a doubt, the ultimate cosmic treasure hunt. I mean, this is a story that's part astronomy, part high-stakes engineering, and a whole lot of detective work. And it's all about finding literal trillion-dollar assets just floating around in space.
So this really gets to the heart of it, right? This is the big question. Space is just unimaginably vast. And you've got this enormous list of potential targets. So how in the world do you even begin to sift through all those floating rocks to find the one that's actually worth the trip?
And yeah, that number, it's not an exaggeration. As of 2026, we've already cataloged over 35,000 near-Earth asteroids, or NEAs. You have to imagine this giant cosmic haystack full of remnants from the birth of our solar system. And we're in there searching for some very, very valuable needles.
So the very first step is pretty simple. It's all about location, location, location. We basically just ignore the really distant asteroid belt. You can think of that as a far-off, inaccessible mountain range. Instead, we focus on the NEAs, which are much more like our local park. This is the first absolutely critical filter that turns a ridiculously huge search area into something, well, still huge, but a little more manageable.
Okay, so that brings us to the first real phase of the hunt. Long before we can even think about sending multi-billion-dollar missions, we have to actually find our targets from a distance. We're looking for these tiny, faint specks of light moving against the infinite black of space.
And right away, we hit a snag. The first big hurdle is our own planet. We're trying to look through 100 kilometers of turbulent, swirling air. So even with these massive telescopes, like the ones on Mauna Kea, Earth's atmosphere basically acts like a foggy window. It just blurs the very details we're trying so hard to see. It's a major bottleneck right at the start.
So, how do you find something that's literally pitch black and doesn't reflect any light? Well, you stop looking for light and you start looking for heat. See, out in the cold of space, these asteroids actually glow with their own warmth, kind of like coals in a dying fire. Space-based infrared telescopes can pick up these heat signatures, and that reveals these stealth asteroids that are often packed with water and carbon, which is exactly what prospectors are looking for.
Now, once we get a blip on the infrared scope, we start to refine the map. We bring in the big guns, like the Goldstone radar system, which bounces radio waves off the asteroid to build a 3D model of its shape, its size, and how it's spinning. And what's really cool is that this isn't just for the pros. Even amateur astronomers can jump in, using apps to report sightings and help track these things across the sky.
But look, spotting an asteroid from millions of miles away is one thing. Really knowing what it's made of, that requires getting up close and personal. And this is where the robotic scouts come into play.
You know, you really have to understand the difference here between an estimate and what we call ground truth. A telescope gives you an educated guess, a blurry idea of what's there. Think of it like a fuzzy photo. But a robotic probe that actually goes there and physically touches the surface, that gives you undeniable proof. It's the geological reality you absolutely need before you commit to sending heavy mining equipment.
And we've already seen this in action. NASA's OSIRIS-REx mission to the asteroid Bennu was a total trailblazer. It showed us that Bennu was basically a loose rubble pile. And now a whole new wave is coming, with commercial companies like Astroforge and international missions like China's Tianwen-2. They're all pushing brand new tech like touch-and-go robotics so they can get samples without the huge risk of actually landing.
So you found a few promising candidates. Maybe you've even sent out a robotic scout. Now comes the really critical part, the selection process. How do you decide which asteroid is actually the one? Well, it all comes down to a very, very specific shopping list. Honestly, the best way to think about it is like house hunting. You might find a gorgeous mansion, but if it's sitting on a remote mountaintop with no roads, it's not a very practical choice, is it? In space, that accessibility is measured by how close it is, and by something called delta V.
Let's just quickly break this down because it's so important. Delta V is basically the fuel cost to get to your target. A low delta V is like driving downhill. It's an easy, efficient trip. A high delta V, though, is a serious uphill battle that's going to cost you a fortune in fuel. For any of these missions to make economic sense, the target must have a low delta V. End of story.
All right, next on the list, what is it actually made of? You have to know your ore. Are you hunting for C-type asteroids? These are kind of like wet sponges, full of water that you can turn into rocket fuel right there in space. Or are you going after the really big prize, the M-type asteroids, which are basically metallic vaults that could be holding platinum and gold?
And here is how it all comes together in that final checklist. The perfect target is a nearby NEA with a really low delta V. You want it to be over a kilometer in diameter with a nice, slow, regular spin so it's safe to approach. It needs to contain valuable materials, of course, and have a potential market value of over $1 billion. It's a pretty tough checklist to pass.
Now, of course, this is space we're talking about. It's not exactly a simple walk in the park. The high frontier is absolutely filled with hazards. But the future of the hunt is also being shaped by some incredible new technologies that are designed to overcome them.
And the risks are very real. You have detection risks. These small dark rocks can hide in the sun's glare until it's too late. Then there are the physical risks. When you get there, you find out it's a rubble pile held together by static, and the abrasive dust can just shred your equipment. And then there's the big legal question mark. The Outer Space Treaty says space is for everybody, but who actually owns the stuff you dig up? It's still a bit of a gray area.
But here's where it gets really exciting. The next decade is going to see a complete revolution in prospecting. We're talking about AI that can analyze data faster than any human ever could. We're talking about swarms of tiny, cheap microprobes that will map asteroids together, almost like bees scouting a field. We're even looking at wild concepts like optical mining, using focused sunlight to figure out what's inside without ever having to land.
So, to wrap this all up, the path from just a faint little twinkle of light in a telescope to a prime target for harvesting follows this clear, methodical journey. You have to spot it from afar, then you scout it with a probe for ground truth, and finally, you select it based on that really strict set of criteria. This whole process is what sets the stage for the next great phase, industrial extraction.
And that leaves us with this final thought. We're getting to this amazing point where we finally have the map and the tools. The thrilling, decades-long hunt to find these cosmic treasures is, for the first wave of targets, pretty much over. But in the grand scheme of things, really, the journey is only just beginning.